The gas law. The ideal gas, kinetic molecular theory. This is the assumption we made to explain the behavior of gases under different conditions. It has to do with how people simplify the reality so as to think about gas thoroughly. First, gases are composed of very small particles, and these particles are very, very far apart. As a result, volume of gas particles compared to volume of the spaces they occupy are negligible. The forces of attraction between the particles are negligible too, basically saying that particles have kinetic energy, so they move around freely. All collisions between particles as well as the walls of the container are perfectly elastic. That means there's no energy lost due to the collision. The average kinetic energy of the particles is directly proportional to the Kelvin temperature of the gas. Based on those assumptions, we can work out what will affect these gas particles: pressure, volume, amount, basically how many moles of gas particles there are, and temperature. Now, let's look at temperature first. The unit of temperature used in gas law is Kelvin. The guy who came up with Kelvin scale, William Thomson, attended university from the age of 10 and went to Cambridge at the age of 17. And he lived the rest 53 years of his life as a professor at Glasgow University. He was buried beside Sir Isaac Newton right now. The conversion between Kelvin and Celsius is simply adding 273.15 degrees to our normal temperature in degrees Celsius will become the Kelvin scale temperature. 0K is the lowest temperature theoretically possible, which is the absolute zero. At 25 degrees, the temperature in Kelvin scale instead is 298.15 K. Okay. At this temperature, the reason we call it absolute zero is because at this temperature, all molecules and atoms have minimum kinetic energy. So basically, all particles stop moving. Pressure. What is the definition of gas pressure? It's defined as force exerted on a unit of area of a surface by the particles of a gas as they collide with the surface. The normal unit of pressure is Pascal, which is actually defined as 1 Newton on a square meter. In gas law, the unit is kPa, and therefore you need to, if you're given Pascal, you have to multiply that by 1,000. Our normal atmospheric pressure is 101.3 kPa. You can imagine for the same amount of gas particles, if they are full of energy, they will exert higher pressure to the container. For volume, we are already quite familiar with this unit. You're required to adapt at its conversion. In gas law, volume must be meter cubed. Okay? Now pause the video and try converting 700 ml into these 3 different units. And here is the answer. Mole, the amount of gas particles present will obviously affect the other properties, and the unit for mole is the one and only mole. Now, how will those quantities affect each other? Will high pressure result in higher kinetic energy and therefore higher pressure, or higher volume? Will there be, if I have a larger amount of gas, will there necessarily be at a higher pressure? Or what if temperature is lower? Now, with all of these questions in mind, the ideal gas equation comes to the rescue. Okay? So it captures the relationship, especially the numerical relationship among different quantities. The universal gas equation also gives us a constant that we haven't met before. And where can we find it? You guessed it, it's on your data book. Okay? Pay attention to the unit of this particular constant. It is very specifically 8.31 joules per mole per Kelvin, which means that when you use the ideal gas law to do some calculations, you will always need to make sure that your units are correct, because the unit of the constant is already set for you. Temperature must be converted to Kelvin before we do the calculation. It's actually one of the most common mistakes related to gas law, forgetting to convert temperature to Kelvin. Now, we mentioned before that our gas laws actually has limitations. An ideal gas is defined as one that obeys the ideal gas law, which means that for 1 mole of ideal gas, its pressure at all times times volume at all times divided by the constant R, and temperature will always equal to 1 at all times. However, real gases deviate to some extent. Here's an example of the behavior of nitrogen gas under different temperature and pressure. And you can see that the gas behaves most like ideal gas when at low pressure here. It also really deviates as the pressure increases, right? On that side, all 3 lines would deviate from the ideal gas. Also, the gas behaves most like ideal gas at high temperature. This one at 1000 K. It's the most closest to this ideal gas line, which should be a constant 1 at all times, since the y-axis is PV over RT, right? And however, at low temperature, it actually deviates more and more. Why does high pressure force real gas to deviate from ideal gas? When we are stuck with a model and realize our observation doesn't fit the model, we need to challenge the assumptions. Okay? We assume the volume of gas particles are negligible. However, with increasing pressure, which means volume decreases, and as a result, as volume continues to decrease, the size of gas particles becomes significant. Therefore, the volume of 1 mole of real gas under high pressure is larger than the predicted 1. Similarly, why does low temperature force real gas to deviate from ideal gas? We assume that there are no attractive forces between the gas particles. That's almost true at high temperature, because the kinetic energy at high temperature conquers the intermolecular forces that tend to grasp and stick the gas particles together. However, low temperature means low kinetic energy, means the particles already don't have much energy to run around and run away from each other, so they become more sticky due to intermolecular forces at low temperature. And as a result, our assumption, as exemplified by this 200K curve, it breaks from low pressure to high pressure.